The ocean is a vast and complex body of water, covering over 70% of the Earth's surface. Its depths are varied and mysterious, harboring countless forms of life and fascinating geological features. To understand ocean depth, it's essential to explore the various aspects of the ocean, including its structure, zones, life forms, geological activity, and human exploration. The ocean is divided into different zones based on depth and light penetration. The shallowest zone, the epipelagic zone, ranges from the surface to 200 meters in depth. It is also known as the sunlight or photic zone because it receives enough sunlight to support photosynthesis. This zone is home to a vast majority of marine life, including phytoplankton, which form the base of the marine food web. Most of the ocean's primary productivity occurs here, making it a critical area for fishing. Below the epipelagic zone lies the mesopelagic zone, extending from 200 to 1,000 meters. Known as the twilight zone, it has diminishing light as depth increases, with minimal light at the lower boundary. This zone contains creatures adapted to low light conditions, such as lanternfish and bristlemouths. Many organisms in this zone are bioluminescent, creating a hauntingly beautiful display in the darkness. Further down, between 1,000 and 4,000 meters, is the bathypelagic zone, often referred to as the midnight zone. It is completely dark, except for the light produced by bioluminescent organisms. The pressure is high, and temperatures are near freezing. Despite the harsh conditions, species like giant squids and anglerfish have adapted to survive here. Beyond the bathypelagic zone lies the abyssopelagic zone, ranging from 4,000 to 6,000 meters deep. Also known as the abyssal zone, this area is devoid of light and has extremely high pressure, cold temperatures, and sparse nutrients. However, specialized organisms such as deep-sea polychaete and various echinoderms have evolved to thrive in these conditions. The deepest part of the ocean is the hadopelagic zone, found in ocean trenches and extending from 6,000 to 11,000 meters. Named after Hades, the Greek god of the underworld, this zone experiences incredible pressure, with temperatures just above freezing. Life forms here are adapted to the extreme environment, including certain types of fish, tube worms, and microorganisms. Measuring ocean depth has evolved over time, employing various techniques. One of the oldest methods is lead line sounding, which uses a weighted line to measure depth. However, this method is limited by the length of the line and the effort required to manually retrieve it. Modern techniques include echo sounding, which uses sound waves to determine depth. In this method, a sound pulse is emitted, and the time it takes to return is measured, allowing for accurate depth readings. Multi-beam sonar is another advanced method, using multiple sound beams to create a detailed map of the ocean floor. It provides high-resolution data and is commonly used in scientific research and underwater mapping. Satellite altimetry, which measures the height of the ocean surface from space, can also infer seafloor features by observing variations in sea surface height caused by gravitational anomalies. The ocean floor is not a flat, featureless plane. It includes diverse geological formations. The continental shelf, for example, is the extended perimeter of each continent, submerged under relatively shallow water. It is rich in resources such as oil and natural gas. The continental slope is the steep descent from the edge of the continental shelf to the ocean floor. Abyssal plains, found at great depths, are flat, vast regions of the deep ocean floor, covered with fine sediment and occasionally punctuated by abyssal hills. Mid-ocean ridges, which are underwater mountain ranges formed by tectonic activity, are sites of seafloor spreading where new oceanic crust is created. Ocean trenches, the deepest parts of the ocean, are formed by subduction zones where one tectonic plate is forced under another. The Mariana Trench, for example, is the deepest known part of the ocean, reaching depths of about 11,034 meters, 36,201 feet. Life in the ocean varies dramatically with depth due to differences in light, pressure, and temperature. In the photic zone, which supports the majority of marine life, you find a wide range of organisms, including fish, marine mammals, sea turtles, and a variety of invertebrates. As you move into the twilight zone, organisms adapt to low light conditions. Bioluminescence is common, serving purposes like communication, predation, and camouflage. In the midnight zone, creatures like anglerfish have adapted to complete darkness and high pressure. The abyssal and hadal zones, though extreme, host specially adapted organisms like tube worms that thrive around hydrothermal vents. These vents provide energy through chemosynthesis, supporting unique ecosystems in the absence of sunlight. Human exploration of the ocean depths has been a challenging and ongoing endeavor. Early exploration was limited to coastal regions, with lead-line soundings providing initial depth measurements. Modern techniques, such as sonar, submarines, and remotely operated vehicles, ROVs, have revolutionized deep-sea exploration. One of the most notable achievements was the bathyscaphe Trieste reaching the Challenger Deep in the Mariana Trench in 1960. More recent expeditions, such as the Deep Sea Challenge led by James Cameron in 2012, continue to push the boundaries of what is known about the ocean's depths. Organizations like the National Oceanic and Atmospheric Administration, NOAA, and the Schmidt Ocean Institute are at the forefront of ongoing research and exploration. The ocean's depth plays a crucial role in the global climate. The ocean absorbs and stores solar heat, distributing it globally through currents. Deep ocean currents, part of the global conveyor belt, help regulate climate by transporting warm and cold water across the globe. Additionally, the ocean acts as a major carbon sink, absorbing CO2 from the atmosphere. Deep ocean layers store carbon for long periods, influencing atmospheric CO2 levels and, consequently, climate change. The interaction between the ocean and the atmosphere also drives weather patterns, with phenomena like El Niño and La Niña resulting from variations in ocean temperatures that can have widespread climatic impacts. Despite the progress made in understanding the ocean's depths, there are still significant challenges and future directions to consider. Exploring and studying the deep ocean is technically demanding and expensive due to extreme pressure, low temperatures, and darkness. Environmental concerns, such as pollution, overfishing, and deep-sea mining, pose threats to marine ecosystems. There are also scientific gaps, as large portions of the ocean remain unexplored, and many species are yet to be discovered. Future research and exploration are likely to focus on developing advanced technology, such as autonomous underwater vehicles, AUVs, and more robust ROVs. There is also a growing emphasis on sustainable practices to balance resource extraction with conservation efforts to protect deep-sea ecosystems. International collaboration will be crucial, with countries and organizations sharing data and resources for comprehensive oceanographic studies. The ocean's depth is a frontier of immense mystery and importance, holding the key to understanding Earth's climate, biodiversity, and geological processes. Despite the challenges, advancements in technology and international cooperation offer promising prospects for unveiling the secrets of the deep ocean, ensuring its preservation for future generations.